Good afternoon, everyone. Thanks for joining us. We'll give others a few minutes to join and then we'll go ahead and get started. Thank you. All right, let's go ahead and get started. Good afternoon, everybody. Welcome to Data Engineers Lunch 74. I'll be your host this afternoon. My name's Akwi Ohiri. Our presenter this afternoon, special guest Alex Merced. He'll be going over table format comparisons, and we'll get into that very shortly. Our co-organizers for this event are Rahul Singh and Arpan Patel. We are looking for speakers and sponsors for this event. If you're interested in either of these opportunities, please reach out to Arpan at the email listed below. Here at Data Community DC, we're part of a larger community that believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome, and we expect respect to be given to all. Data Community DC is actually made up of a lot of different groups, all usually focused around data. And you can find out more about all the various different groups and events at the websites listed below. Here at Data Engineering Lunch, we cover everything from the ingress and egress of data and everything in between. We cover everything from databases, ETL, data wrangling, and all the tools and processes in the data engineering world. At this point in the event, we'd like to invite people to introduce themselves. So if you're new to the event, please just drop a comment, what you do, what you're interested in learning, and any other information. We're glad you're here. Group rules: if you have a question, ask it. I like to defer to the presenter. Some presenters like their questions asked as the presentation goes along. Others like their questions asked in a break during the presentation. Please be respectful of your presenter's wishes. Also, please be polite and courteous to everyone. And of course, share what you know with us. Here at Knot, we build and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. GW is a sponsor for this event when we do have in-person meetups. So we'd like to say a big thank you to them. Also, we have some institutional and organizational sponsors listed here. Thank you to them as well. If you have any announcements, jobs, meetups, hackathons, conferences, or classes, please mention them in the comments below, and please attach any associated links, and we'll be happy to go through those. Also, we are hiring here at Anant. If for more information on the positions we have available, please visit the careers.anant.us website listed below. Please also visit our events website where we have our weekly events listed there and any other upcoming events you want to stay tuned to what we have coming up. And then finally, we have our latest runbook out. This is runbook 8. It covers high read and write latency and then fixing large partitions for Cassandra. Please do check that out while it's still available. We'll have another runbook out shortly, at which time this one will no longer be available. So please make sure you get yours as soon as possible. And then with that, I'd like to hand it over to our presenter for today. Over to you, Alex.
Hey everybody, my name is Alex Merced. I'm a developer advocate at Dremio, and today we're going to be going over a table format comparison. This was actually a presentation I did a few months ago at one of our subsurface meetups. But if you follow the world of table formats are constantly changing and evolving. It's a really exciting hot space. So basically today's version of the presentation will reflect many of the changes that have happened in nearly the last couple months. So it should be a good time. Again, my name is Alex Merced. I'm a developer advocate here at Dremio. Particularly, I'm on the tech advocacy team, where we focus on sort of promoting a lot of different open source technologies around the data lakehouse, as Dremio is a open lakehouse platform. You can follow me on Twitter, so you can anytime I speak about data lakehouse related topics, you can find out about them over there at AM Data Lakehouse on Twitter. But with that, let's get on to the show. So today, what we're going to be talking about is what's a table format. So the first thing we're gonna do is just kind of establish like, what is this thing that we're talking about? We get it that there's this Iceberg Delta Lake Hudi thing that everyone's really excited about, but what is it? The question is gonna be like, why do we need a new format? Because wasn't there this Hive thing that we were all using before that we were all still using? What's wrong with that? And then what are these 3 newer table formats? What are they bringing to the table? Like, what is the niche they're trying to fill? And then we're going to talk about a comparison. So we're going to talk about like the differences of features, differences in like read and write support at different engines. They're sort of like open source communities, and so forth and so forth and so forth. So let's continue on with that conversation. So first, let's talk about what is a table format. And this matters particularly in the world of data lakes and data lake houses. So again, just to kind of make sure we're all on the same page with the terminology, data lake, again, this big place where we put all our structured and unstructured data before we possibly ETL it to a data warehouse. Data lakehouse, where we take that data lake, the place where we store all our data, and instead of moving it to a data warehouse, we're doing operations right there in the data lake using a variety of different tools, so that way you get the best of both worlds. You get sort of like all the features you would expect in a data warehouse, but you get the cost point and the openness that you would expect on a data lake. So in that data lake house world, what happens is that we generally take tables for granted in other spaces. So when I use like a Postgres database in the OLTP world, in the transactional side, I just make a table. I just make a table. I can query that table using SQL. I just kind of take that for granted. I'm not really thinking about how under the hood Postgres is representing that data on the hard drive or on wherever the data is being stored. Same thing in a data warehouse. If you ETL your data into a data warehouse, you have tables. You kind of take for granted that they exist. You don't really see what's going on under the hood. But in the data lake world, we're dealing with the direct sort of files. So I may have a data set that's broken up into 1,000 Parquet files. But when I run my analytics, I don't want to run analytics on just one Parquet file. I want to run analytics on the full 1,000 Parquet files and treat them as sort of one data set. And so we need some sort of abstraction to kind of overlay on top of that. So that way, whether I'm writing a Python script or writing an SQL query, that I have this concept of the data set, of the table that I can refer to, instead of having to sit there and say, hey, this file, this file, this file, this file, this file, this file. And that's the purpose of a table format on the data lake house. It's going to be this layer that's going to allow us to say, this group of files over here is one data set, this group of files over here is a different data set, and allow us to kind of run SQL scripts and things like that, like we're used to in other places, in more traditional databases and data warehouses. So what happened is that originally, like when the data lake kind of first came up and you had like Hadoop, everyone was like running Hadoop clusters, you would use the Hadoop sort of framework, MapReduce, to run operations on the data lake. And that required you to write these sort of complex JavaScripts. You had to define your data set file by file. So you say, hey, this group of files is what I'm doing this script on. It wasn't the most convenient thing in the world. So Facebook develops this thing called Hive, the idea being, let's make this a lot easier. Instead of having to write these sort of custom JavaScripts every time you want to do analytics on these large data sets in your Hadoop storage, wouldn't it be nice if I could just write an SQL query, and that SQL query gets translated into one of these MapReduce scripts, and it just makes it a lot easier for people to run analytics. But in order for you to write SQL, you need tables. Like I have to have some sort of idea, be able to say, hey, select all from this table. So one of the challenges in creating Hive is that they determine like, okay, how do we recognize a table on your data lake storage? So the approach that Hive took was to look at it from a directory approach. So we'll say, hey, this folder is the table. Any data in this folder is part of that table. Any subfolders in that folder are a partition of that table. And generally like the folder names would match sort of like their partition values and things like that. And this allowed Hive to be able to sit there and just take a look at your hard disk, your files, and be able to recognize, okay, these are the files that are part of that particular table because they're in the folder for that table. And that did the job. Okay, you were able to write SQL statements that were translated into like MapReduce scripts, and again, that's all evolved since then. But it solved the problem at hand. And there was a lot of pros to this evolution. So the fact that we're now able to recognize tables on the data lake and run operations on them. The pros is, since Hive was the only thing at the time, it became the de facto standard. Everyone uses Hive. And when everyone uses the same thing, that means generally everything supports Hive. So one of the still like the best things about using Hive is everything supports Hive. Okay, and it's still pretty much a de facto standard. Okay, since I don't have to define my data set, always like the concern is if I just say these 1,000 files are my table, well, do I really want to scan all 1,000 files for every query? But Hive allowed you to use partitioning. So you were able to kind of create those sort of subgroupings of files or sections of your table and write queries that only query the partitions you really need. So you were able to have those more efficient access patterns with the convenience of tables. It wasn't perfect, but it certainly was better. It was file format agnostic. In that folder that defines your table, they could be whatever kind of file type you want. It doesn't have to be all Parquet files or ORC files or Avro files or JSON or CSV. It was just like whatever files are in there, that's part of your table. Okay. You could atomically update a whole partition. So you did have safety if you were to update a partition. So if I wanted to update, let's say I have my data partition by month, and I want to update 1 month's worth of data, I could do that atomically. Okay, it would basically just rewrite the partition and then swap it out, and that was all really well and good. And more than anything, it provided us a single answer to what is the data. Okay, because what could happen back if you were writing those MapReduce scripts and naming those files one by one, 2 different people trying to run analytics on the same data might choose slightly different sets of files. And now the analytics don't match, there's inconsistencies. By having sort of a defined table, and we know, like, hey, this is the table, this is the data, everyone's running analytics on that same data set. And there's a lot to be said for that level of consistency. Cool. But again, it wasn't all sunshine and rainbows. There were definitely some cons, which is going to be why we lead to all these newer data formats. Smaller updates are really inefficient. So again, the way Hive generally did updates was at the partition level. So what if I only want to update 1 record? Okay, in the best case scenario, I'm rewriting that entire partition to update 1 record. Not the most efficient thing in the world. Okay, now if you want to change data in multiple partitions, that was kind of hard to do safely, because you might be doing the update in 1 partition, and then someone else might be updating another partition, and then by the time you get to that update, you now have conflicting changes or unexpected things happening. So there was all these sort of challenges in trying to get those sort of guarantees of atomicity when you start doing multi-partition updates. And again, generally, if you're doing multiple jobs on the same data set, especially if you're writing, hard to do safely. Just wasn't really designed with a lot of that in mind with the limitations at the time. Okay, because Hive was 2010. that it was created. All of the directory listings needed for large tables take a long time. Again, it was really dependent on that folder. So basically the way it would discover, hey, what's inside the table, it would list everything inside that folder. Every folder, every file. Then it would go inside those folders and then list every file in those folders until it figured out every file that's part of that table. Okay, and then depending on your partitioning, you're scanning several of those partitions and it has to go through each of those files, open them up, read them, close them, then open up the next one, then read it, then close it. So all those file operations really added to the time it would take to get like a scan done. Okay, so really long queries. And when it came to partitioning, it was it could be a little awkward. Okay, so here's an example. You have a timestamp. So I have a timestamp field for sales. Okay, so every sale has a timestamp. Okay, but I want to partition the table by year and month. Okay, so what I would have to do is I couldn't use the timestamp field. I would have to create another field derived from that field. So say, hey, take this timestamp and make it into a month, and take this timestamp and make it into a year, and then partition the table by those two new columns, which is fine. That does the job. But the problem comes in for the data consumer. Okay, if I'm someone just querying the table, I'm just thinking, I just want to query the data from this timestamp to this timestamp. And if I do that, I'm going to end up in a full table scan. It's going to scan every file. Because what I had to do was add an additional filter saying, not only do I want to scan between this timestamp and this timestamp, but I also want to scan for things within this month to this month and this year to this year. So that way it actually takes advantage of the partitioning. So if someone didn't understand how that table was actually engineered and how it was partitioned, they could write queries that could accidentally end up being really slow full table scans. So solving that problem was also another big thing we want to solve as we evolve from Hive. And generally, whenever you wanted to update your table statistics, you would have to run these analyze queries. So instead of like just having the stats available to you, you would periodically run analyze and it would read the whole table and gather you all sorts of statistics. So until the next time you ran analyze, your statistics were kind of stale. They weren't kept up to date as the table changed. So that's something else we would like to work on. So we want to resolve all these issues. So what's going to happen is that different table formats tackled these issues, okay, and said, okay, hey, we still want you to be able to recognize tables on your data lake, aka data lakehouse, but each of them sort of had a slightly different approach to it. They're all trying to solve the same problem. They're all trying to kind of converge on sort of a similar solution, but they all do take slightly different approaches to it. And that's Apache Iceberg, Apache Hudi, and Delta Lake. And so these are the three sort of table formats of this next generation. Okay, and that's sort of like the big hot topic nowadays, because right now you're starting to see more and more momentum for this idea of a data lakehouse. And if you're building a data lakehouse, you're going to want not only the tools, but you want your tools to be able to perform fast as possible. And your data lakehouse table format provides this layer of metadata that allows the tools that you interact with that data to perform a lot faster and gives them all sorts of really cool features. So you're going to want that. The question is like which one to choose, because you don't want to write all your data 3 times and have all your data sitting in 3 different formats. You kind of want to have a format that you kind of commit to, and then hopefully that one is a good long-term choice, because if not, then you'll have to migrate all that data and rewrite all that data later on and configure all these things again. So this is sort of the big choice that's confronting a lot of people, a lot of data architects, as they decide, okay, while we build out this data lakehouse thing, this thing is really like the core. Which one should I choose? Okay. That's why, again, such a big, high value topic. Okay, so now let's talk about like how each one sort of is architected and sort of like their general modus operandi. So first let's talk about Apache Iceberg. Okay, Apache Iceberg originated at Netflix. And essentially the way Apache Iceberg works is that it generally has a metadata tree, meaning instead of having just like all your metadata sort of kind of clustered together in similar files, there's actually 3 types of metadata files. So there's your metadata file, your manifest list, and your manifest file. And instead of the engine just reading the files on the file, like either on your HDFS or your cloud storage, your object storage, instead of just reading the files and figuring out, hey, these are the files I need to read, what it does, it uses a catalog and uses the catalog to kind of figure out, hey, what is the right metadata file to look at? So it has like this sort of unique structure that really represents like a clean break from the way Hive works. So instead of relying really on the directory and how the files were laid out in a folder, it's going to rely heavily on this metadata and how this metadata actually lists individual files to go scan. So again, you have the metadata file. These are like your table level metadata file. So like think of it as like a global metadata file. So it tells you this is the table, this is the current schema and the previous schemas, this is the current partitioning scheme and the previous partitioning schemes, sort of all this sort of, these are the current snapshot and all the previous snapshots. It has all this sort of current and historical data about the table as a whole. And generally that's going to be where the engine goes first. So the engine goes to the catalog, says, okay, where is this table? The catalog points it to the metadata file. And then the metadata file will point it to a snapshot, which is represented by these manifest list files, which are snapshot level. So instead of listing historical stuff, they just list, hey, this current snapshot that this metadata manifest list represents this partition scheme, this schema, and basically this snapshot's made up of these groups of files. Okay, so instead of having one list of files right here, what they do is we're going to actually have an extra layer. So we'll say, hey, there's these big chunks of files that make up this snapshot, and each chunk is referred to as a manifest file. So each manifest file is a chunk of files that are part of a particular snapshot or multiple snapshots. So again, basically you have your global metadata, your snapshot level metadata, and then you have your groups of files. And then at each level, the engine is getting metadata in each of those to start trimming down what it's going to look at. So first it'll trim down groups of files and say, okay, I don't need to look at this group, I don't need to look at this group. And then when it goes into those manifests, it can then start getting rid of individual files, saying, I don't need to scan this file, I don't need to scan this file, until it gets down to its sort of the actual number of files it needs to scan, giving you sort of your trimmest number of files you need to scan. So that's generally like the methodology of Apache Iceberg. So you have different metadata that's available at different layers, which allows you to kind of do extra, more high-level operations earlier on to reduce the amount of more fine-level operations done later on to make things faster. So that's sort of the Apache Iceberg approach. So it doesn't rely on where the files are at all. They don't have to be laid out in that sort of, there's a folder and then subfolders with partitions. Doesn't matter where the files are. Okay, as long as they're in these lists, these manifests. Then you have Apache Hudi. Okay, now Apache Hudi and then later on Delta Lake, they both still adopt that like Hive layout. So they still have the folder and then the subfolders with like your different partitions. But generally what's going to happen now is that you're going to have all these metadata files, these different files that get created throughout this structure that provides the engine extra data to kind of understand like what are the differences at different points in time. So Apache Hudi works with this big timeline concept. So basically it tracks everything on a linear timeline. And so basically every operation we can tell, okay, hey, did it happen here? Did it happen there? This happened before this, allowing you to kind of really sort of piece together what you may want at a particular time. Okay. Now, again, it's directory based. What's going to happen is that you're going to have these every file is going to have a timestamp, and there's going to have log files that actually like illustrate those changes from commit to commit. Okay, but everything's kind of having this sort of timeline superstructure. And when it comes to like additional file pruning, what's going to happen is that there's this metadata table that's now on by default, but can be turned off depending on sort of your needs of a particular table. But the metadata table will have like indexes for different columns, and you can use those indexes to then like figure out, okay, we don't need this file, we don't need this file, we don't need this file, and do those kind of sort of file pruning operations at that level. So you're gonna, and again, that's gonna be the theme here. All three formats, they're trying to provide metadata to, one, activate features like time travel. So you can see here we have a linear timeline, which makes that time travel thing sort of very sort of clear how you would do that. But also they're gonna provide metadata to allow engines to say, okay, I don't need to scan these files. So that way, because there's two ways to speed up a query. You can either have more processing power, but more processing power means more costs. Okay, and we all definitely don't like seeing that cloud bill at the end of the month. And then the other way is to do less stuff. So if I scan less files, my query will go faster, and I reduce my compute and I reduce my costs. So all three formats are really trying to figure out how to most efficiently sort of like narrow down those files that you need to scan. Okay, so again here, again you have basically your timestamp like data files, and then you have your log files that actually illustrate those changes, and then your metadata table that's like separate to allow those sort of file pruning operations. Then you have Delta Lake. And in Delta Lake, the way it works is that you have these commit files, okay? They're called Delta logs. Each Delta log represents one commit, and basically it tracks the changes from the previous Delta logs. So it's kind of intuitive, kind of feel like if you think like a Git, when I go from one commit to the next, each commit is just tracking the changes from the previous commit, very similar. So in a sense, you can recreate the table by applying all these commits in sequential order, okay? And then that's basically how, and then you can go back and like revert to a previous commit, and then that's where your time travel comes in. So in Apache Iceberg, you're able to go to a previous snapshot, a different manifest list. In Hudi, you can go to different points in your timeline, and in Delta Lake, you can go back to previous commits. So they all enable that have that time travel very center to their architecture. But essentially, these commits are just basically saying, okay, hey, from this commit to this commit, these data files were added to the table. These data files were removed from the table. And then that's how it's able to figure out which files are part of the table before it begins any actual pruning. Now, to speed things up, what you can do is every once in a while, you can make a checkpoint. So in this case, you see here, like those 3 commits. And instead of having them each be an individual Delta log file, these commits were then turned into a checkpoint. So this checkpoint then summarizes the net effect of these 3 commits. Okay, and so now going forward, it doesn't have to go commit. It can just start from this checkpoint, then start going commit to rebuild the table. Yep, and then again, in these commits and in these files, there's also going to be like indexes on different columns and stuff like that. And just kind of similar to the metadata table in Hudi, it can use those indexes to begin sort of pruning data files. So again, it's very similar story, which format, because they're all trying to solve the same problem. Like, how can we make sure that when an engine has the right data so they can plan the most efficient query possible? So those are sort of your 3 contenders in the world of data lakehouse table formats. Well, let's talk about the features. And before I show like all the different features, one thing that you always kind of keep in mind is like all 3 of these are in constant development. So all of them are constantly adding features. So like this looked a lot different a couple months ago. It looked a lot different even before that. So over time, like features that one has that the other one hasn't, they're all kind of gonna get to that feature parity because that's just the nature of these things. But here's sort of the current state of things at the moment. They can all provide you ACID transactions. Okay, so in that case, you want to go atomically update a single record, a whole partition. You want to go delete. You want to do updates. You can do all that safely. Okay, which was not something you could do with Hive. Like that was like sort of like the initial impetus of doing all this. And I did mention that Iceberg was created at Netflix. So just to kind of give you the whole story. Apache Iceberg was created at Uber, and Delta Lake was created at Databricks. Just to give you the full lineage there. But ACID transactions. So that was like the big impetus. We want to be able to do ACID transactions. We want to be able to do stuff with the data safely, other than just read it. Partition evolution. This is a feature that's currently unique to Iceberg. And what this feature does is that it actually allows you to update your partition scheme. The nice thing about that is you don't have to rewrite your table. So if you were partitioning your data by year, but then later on you want to partition it by year and month, you could change that and it will partition the data by that new partition scheme going forward without having to rewrite all the previously partitioned data. It would just create 2 separate query plans. So it'll plan the data that was partitioned by year will be planned separately than the data that was partitioned by month and year. And this way you save yourself the time of having, again, rewrite the whole table. And you can still create efficient query plans. So there's partition evolution. So that's a thing that's in Iceberg, currently not in Hudi or Delta Lake. Then there's schema evolution, which actually, for the most part, you'll see later on, they're all on track. So this actually this should be a check mark over here for Delta Lake. And then yeah, they're pretty much all at parity. Like in their most recent releases, all 3 of them are pretty much at parity, where you can pretty much add a column, delete a column, drop a column, update the names of columns, change the orders of columns in certain contexts. So for the most part, that they're all on parity there. You can pretty much change whatever you want going forward with your data. Okay, so you're not stuck with a particular schema. Your table can evolve as your needs evolve. They all have time travel. So with all of them, you can go back to previous snapshots. That is limited for all 3, because what happens is there's going to be cleanup operations. All 3 tables, there are times where you need to maintain them, because if you keep all snapshots ever made, all commits, all timestamps, what's going to happen is you're going to have a huge buildup of files and metadata. So generally, periodically, you'll want to go up in there, and it could be referred to as expiring snapshots, as using the vacuum command. There's different frames for it, but the idea is you're going to go back and say, these previous changes, I don't need to go back to anymore. So let's not hold all that stuff. So when you do that, those old expired snapshots, you're not going to be able to time travel to. But you can decide how far back you want to be able to go to. So you can be like, okay, hey, let's expire everything back from like, the last 10 days, or let's not leave anything historically. It just depends on your needs. But you will have that time travel feature, which is really useful, especially when you're trying to do quality control and double check, hey, there's, make sure that all your ingestion was correct, or if you want to do testing of like machine learning algorithms, and you want to make sure you test them on consistent data. So you want to use the exact same sort of picture of the table that you used on the last test. Okay, merge on read. Okay, so merge on read is an option where you can set table or specific table operations to, instead of having to so let's say I want to rewrite one record. Okay, the default is called copy on write. So I want to update one record, which is in this Parquet file of 1,000 records. So by default, generally you're going to have copy on write. So it's going to rewrite that entire Parquet file. It's going to rewrite all 1,000 records, even though you only updated one record. Okay, that can make your writes take longer, which could not be the most ideal thing, especially when you're doing streaming. So with Iceberg and Hudi, okay, what you can now do is you can specify tables to handle those types of operations as merge on read. So instead of rewriting the entire Parquet file and all 1,000 records, what it'll do is it'll keep the original Parquet file or whatever file with 1,000 records, and then write a additional file that just says, hey, just so you know, in that file, this record should be ignored. So that way that record is deleted. And then what's going to happen is on the read, you reconcile that. So basically what you do is you spend a little bit more time on the read to save yourself a whole lot of time on the write. Okay, so currently Iceberg and Hudi both have merge on read capabilities. Delta Lake not yet. Z order, okay, on the newest releases of Iceberg and Delta Lake, they have added Z order. Hudi's had it for the last few releases. So so they all have Z order features where you can do like things like Z order sorting to help optimize your data, especially for data where you're querying on multiple fields. So basically they all have Z order support. Then there's Project Nessie support. So Project Nessie is another open source project that offers a really, really sort of a cool proposition. What it is, it's a service you can run that provides you Git-like semantics. So like the ability to like branch your tables, merge your tables. So this is really useful when you want to do multi-table transactions. So something you're really used to on data warehouses. So in data warehouses, I can be like, okay, begin transaction, end transaction. And then I might do operations on like 5 tables, but all the transactions on all 5 tables will be committed at one time. So it seems like all those changes occurred at the same time. To do that on the data lake, on the data lake house, it's a little bit tricky. And this is where Project Nessie comes in. You're able to create a branch, do all the of your catalogs of all your tables, and then you can do operations on any tables you want, and then merge that back into the original or main branch. And then basically you have that same effect where basically to your data consumers, it's as if all those updates occurred on all those tables at the same time. Currently, there's only full support for Project Nessie for Iceberg. There is a pull request to later have support on Delta Lake. I'm not aware of any work currently being done on it being supported by Apache Hudi, but that's Project Nessie. So right now, Iceberg supports that, so you can have that sort of multi-table transaction element with Iceberg. Okay, breaks from the Hive layout. So again, kind of mentioned this a little earlier in the sense that Hudi and Delta Lake both still rely on, so they don't necessarily have to have like a catalog. Because what they can do is they can just scan a folder because they're going to assume that the files are laid out in that Hive style. Okay, so basically you have the folder that's the table and then all the subfolders, which are partitions. Okay, the downside is when you're talking about cloud object storage. So on like something like Amazon S3, everything that's inside what you're used to thinking of as the same folder, on S3 it's the same prefix. Okay, and generally Amazon or AWS and other cloud object storage providers, they will throttle the number of requests for files under the same prefix. So if you have a partition that has a lot of files, that could result in throttling for very large queries where you're scanning all the files in that particular partition. And there's not, Iceberg doesn't rely on that. So you actually have a little throttle, a little toggle, like a little setting you can set And what it'll do is it'll split up the same partition over many different like hashes. So that way, all the data in one partition is not in one folder, but it's across several different directories with like hashes. So that way you don't run into that throttling. So that's sort of like the reason why the hay layout thing. Like if you're using Hadoop file storage, if you're using like a Hadoop cluster, then it doesn't really matter how they lay out their files. You're not the performance-wise, they'll be the same. Okay, file format support. Your Iceberg tables could be made up of Parquet, ORC, and Avro files. Apache Hudi, Parquet or ORC, and Delta Lake, just Parquet files. Now, do keep in mind with all of these features is that while the metadata gives you all the tools and the spec gives you all the tools for all of these to take advantage of the features that they have, different engines still have to build their implementation of how they use that format. Okay, so basically, when you take a look at things like performance numbers, you want to make sure you're looking at it on tools that you're using, because oftentimes it's always like based on Spark. But what if you're not using Spark? The performance of Iceberg, Hudi, Delta Lake on different engines and different tools may be completely different than the way they are in Spark, because the implementations will be slightly different. So keep that in mind when you see like a lot of these articles that talk about like performance and whatnot. Question is like, what tools you use, and also again that each table can be, each format has a lot of different settings you can set, little knobs you can turn to get better or worse performance depending on your use case. And that's another thing you don't see a lot, like what are the knobs they turned and how do they turn them to kind of really kind of get apples to apples comparisons. So just keep an eye on that when you see a lot of those kind of articles. Okay, so schema evolution. So again, the ability to update how the schema of the table is. Okay, so generally at this point they're all at parity. Like the only minor difference is like Hudi currently you can do schema evolution just from Spark, but as far as what you can do for all three, you can add column, you can drop a column, you can rename a column, you can update a column, reorder a column. So they're all like in a much better place than they were at the beginning of the year. So like I said, generally over time, most of these are going to all come up to feature parity. So so again, we'll talk more about like sort of like then, well, if eventually they're going to have feature parity, then how do I know which one to choose? We'll get there. We're going to talk about that. Okay, partitioning. Okay, now partitioning, here's where you do see some really interesting differences in how the three formats operate. Okay, so again, Iceberg is the only one with partition evolution. So it's the only one where you can change your partitioning without rewriting. Now, basically, what you can say for the other formats though is they'll say, okay, well, that's not as important because we have these like column indexes, and then we can do pruning and if do more efficient scanning of the table using these other indexes that aren't necessarily as reliant on the partitioning. But why not both, right? Use transforms for existing columns to specify partitions. So let me talk a little bit more about this. So the idea here is the ability to have like certain built-in functions, so that way you can have a column that's sort of tied, or values that are tied to another value. So in Iceberg, you have a feature called hidden partitioning. And the way that feature works is that, let's say I remember that whole situation where I'd have to like additionally query by the month and then query by the year on top of querying by the timestamp. What I can do is I can specify my partitioning in when I create the table and say it's partitioned, and there's these like functions that you can pass the column to. So I would pass a timestamp column to a month function, to a day function. And so instead of having to create an additional column, what I do is that I've mapped sort of like how to transform that particular value, but that is the partition value. So whenever that timestamp column is queried, it's going to take advantage of the partitioning because it knows that the way the table's partition is by month and year relative to that timestamp column. So you get the same benefit, but it's much easier for the end consumer to take advantage of it. And it's much kind of nicer when you're defining your partitions to be able to kind of specify that. Delta Lake, you pretty much kind of end up in the same place. They have a feature called generated columns. This does technically generate another column, so you are actually saving that data in your Parquet files. But what happens is that the files are, the actual data in those columns are automatically generated based on another column. So I could say, I still have to define that month and year column, but I define them as a function of the timestamp column. So I don't have to worry about filling them out. And then when someone queries the timestamp field, since the generated column feature knows that, hey, technically these columns over here, which we partitioned by, are generated based on this column, you still get the benefit. So either way, the idea is that you have that much easier benefit for your end consumer where they don't need to know that you partitioned it by month and year. They just need to know they're querying the data from this timestamp to this timestamp. And the data consumer just queries it and they get the benefit of the partitioning. So right now you can get that benefit in Iceberg and Delta Lake. So that's basically what these check marks here are kind of showing you. Currently not necessarily in Hudi, but again, Hudi has the metadata table and those column indexes, which can still help prune your query based on your filter predicates. So it won't necessarily like eliminate a whole partition worth of files, but it still has those indexes, so it can do some pruning based on your filter predicates. Okay. File pruning. So again, this is going to be more like we've eliminated some files from being scanned through the partition. So we said, okay, we're not scanning these partitions, so those files aren't going to get scanned. That's nice, but we want to take it a step further and get rid of more files, because again, less files you scan, the faster the scan. So in Iceberg, they track column stats as well. And one of those column stats is tracking sort of the upper and lower bounds. Okay, so like what is the highest value, what is the lowest value for this particular column in this data file. And it can use that. So at the query planning phase, it can take a look at each file and say, okay, hey, well, technically I am scanning for all, all customers with an age between 30 and 40. So it can take a look at the upper bounds of the age column in each Parquet file and use it to determine whether this file is possibly going to have any applicable values. Okay, so that min-max filtering can help you reduce the files even beyond the partitioning. And on top of it, if you sort your data, that can even be even stronger. Hudi, again, similar stat, it uses that column stats index. So it really relies on that column stats index that provides similar stats, and then you're limiting it from the get-go for like each individual file. So you're saying, okay, does this file make sense for my query? Does this file make sense for my query? And it narrows that down. Delta Lake also maintains indexes on each column. So again, all three are maintaining data on each column, so that way the engine can narrow down the number of files that you're reading. And then basically that's the way it's handled there. So basically a similar approach, but basically with Iceberg and Delta Lake, you get the benefit of, you can take advantage of the partitioning and the file pruning afterwards. Cool. Query engine support. Okay, so bottom line is like engine support matters because and it's not even necessarily like the number of tools that each of these support. What matters is, do they support the tools you're using? Because you probably have tools that you really like using already with your data lake data, and you want to probably keep using them. Okay, or there's tools that you're exploring you want to use. So there's two levels of that. There's read support, which all three formats have pretty good read support. So generally, most tools, especially most of the most popular tools like Flink, like Spark, you're going to be able to read all three types of tables and be able to read the data, query the data, take advantage of their indexes to get those efficient query plans. For the most part, there's a few exceptions in each column. Okay, I won't go through each one, but I'll leave this up here for like 30 seconds, so that way you guys, if there's a particular tool you want to look at, you can kind of see where the status is. So you can see here, out of the 15 tools I listed, which is not every single tool in the world, there's always more and more data tools that can read these tables. But out of the 15 tools we have listed here, which represent many of the most popular tools, 11 out of 15 support Iceberg, 10 out of 15 support Hudi, 12 out of 15 support Data Lake, and then that's that there. Then we go to write support. Also very important, because nowadays, the reason why we call it a data lakehouse, I mean, we could already read data on a data lake. What makes the data lakehouse extra important is we can do all those extra like update and delete and ingestion, all these other operations we traditionally didn't really think of as what we can do in the data lake. So that means we need write support to kind of make that data lakehouse feel happen. Okay, so when we take a look at write support, the story looks a little bit more different. Okay, so you can see here, based on the 9 tools that we're looking at, because we didn't include tools that didn't have write support for any of them, we didn't include, that's why it's 9 instead of 15. So basically here, again, the most popular ones are going to have write support for generally all three, so like your Flinks, your Sparks. But as you can see here, Iceberg has write support with 8 out of the 9 tools listed. So you can actually write to the table. And again, the level of write support can differ from tool to tool. So there's a difference between, hey, can I, insert a record, delete a record, update a record, do a merge. So it'll vary from platform to platform. Apache Hudi has write support from 4 to 9 of the tools, and Delta Lake has write support from 5 to 9 of the tools. Okay, and that number increased over the last couple months because recently Delta Lake open sourced a couple additional libraries that makes it much more easier to do write support for Delta Lake. So that was like sort of the big change there in the last couple months, which particularly like affected like the Flink support and whatnot, which can now write to Delta Lake. Cool. Now here's where you're gonna see the big difference, because again, people always think about features and performance, and features and performance are important, but these are not stagnant projects. The way they are now is not the way they're always going to be. I mean, all three projects are going to keep adding more features, and they're going to look to each other and say, hey, what's the cool thing that the other project's doing? We could do that too. So you're going to see them get closer and closer to feature parity over time. And performance, anytime someone comes out with a performance benchmark, all three projects are going to be like, how can we improve performance? And again, performance is not just the actual table format, but it's also the tool itself and how the tool uses the metadata, or how that tool's performance is in to begin with. So again, you really have to take a look at performance on the tool by tool basis based on your use case, because it can really vary. So in that case, it makes it kind of really hard to, in the long term, kind of compare based on features and performance, because performance can always be improved and performance can differ quite a bit depending on your specific use case. So what other things? Then you have to kind of think about the long-term sort of governance of the project, sort of like the long term of the project, because what are the benefits of having a data lakehouse? Okay, well, what is like the big value proposition at the end of the day? It's not just analyze data. I could analyze data before. The value proposition here is that one, you're going to avoid the data lock-in of a data warehouse. Okay, so before you'd have your data in the warehouse and you couldn't really, it was kind of locked in there. And the result is you had to pay this huge bill to the data warehouse every month. Okay, if you can operate with that data on the data lake, then that's going to be a lot more affordable. But to kind of keep that sort of one cost structure, you need a competitive playing field where there's lots of tools sort of competing on an even playing field, so that way they keep each other's costs down. And you never get that situation where, hey, you only have one vendor because everybody else left, or basically they're the only game in town, and eventually they're going to raise your prices go up, and there's nothing you can really do about it. Okay, so really what you want is that sort of like that nice, even, open playing field, because that's going to really give you the access to as many tools as possible, and also, again, that long-term sort of like certainty that you're not going to end up in that same situation where you're sort of held hostage to large costs. So with that, that's why it's important to really kind of understand the differences in the communities of the three formats. Okay, and it's not just like, all three formats are open source. So you can see the code, people can contribute to the code, but it goes beyond that. Openness can come to like sort of like who is controlling the project. So Iceberg and Hudi are both Apache projects, okay? And a couple things that you can say about Apache projects is that Apache is very, very like, has a high standard of sort of openness and participation when it comes to not just contributing to these projects, but then also the day-to-day decision making. So like the PMC committees, the committees that kind of oversee and make decisions over the project, generally you're going to need people from like a lot of different companies on them. Basically you can see who's on the PMC on their websites, on the Apache website. So there's a lot of transparency on like who's steering the project, not only who's contributing to the project, and the inevitable code. Okay, Delta Lake's a Linux Foundation project, and Linux Foundation supports lots of open source projects. Great. But at least at the last time I was able to see who sits on the technical steering committee for Delta Lake, they were all Databricks, people from Databricks. And the last thing I can see is there's a commit on the Delta Lake repo where they actually like remove the listing of who. And since then, I don't think there's a way to actually see who's on that committee at the moment. Again, I know they're in the midst of recent changes as they announced sort of even further opening. So hopefully we'll be able to see who's on that committee sooner than later, and then kind of see if the diversity of who's on that committee changes. And the reason being is like, again, the people who sit on these committees, they're going to determine sort of what pull requests get pulled, sort of what features are prioritized, and that's going to determine sort of that playing field between different vendors, which is why that is such an issue. Because again, if a playing field doesn't seem even, then you're going to end up having less people playing in the long run. Okay, so this is a chart, and just to kind of explain how we came up with these numbers. But what this chart is showing you is like the percentage of contributions, GitHub contributions. So this is based on the main public repo for each of these projects. Okay, so some of these projects have like side repos for like side libraries and things like that. This is for like the main table format repository for each one of these that's publicly visible, okay? Because I can't see the stuff that's not publicly visible. But essentially what we did is we took all the commits by each individual, take a look at where they were employed at the time of the commit. Okay, so for example, for Iceberg, it was created at Netflix. So some of the people who were there are now at other companies. So the commits that happened when they were at Netflix were attributed to Netflix. When they were at the commits that occurred while they were at other companies were attributed to other companies. So we actually went in there and, not only took the time to figure out, hey, who was at what company, but when they were at what company compared to the commits that were made to give you sort of the most accurate picture possible. So this was this was a bit of work to put together. But this shows you, like, if you take a look at Iceberg, okay, even though Netflix is the creator, they are by no means a dominant player. Like they're the biggest player, but they're not dominant. They're not 50% of the contributions. So you can see it's a very, very community-driven project. Same thing with Hudi. Uber was where Hudi got created. Again, they're not the dominant player. No one is really has like a 50%. Is really steering this project dominantly. Okay, then we get to Delta Lake, and again, just to give you some footnotes for like if you try to replicate this data, because when you pull that data from like the GitHub API, we did again go make effort to make research and like, okay, who's working at what company? Because there's a lot of people in all three where basically like they didn't like have their company labeled or whatnot. So we did do a lot of making sure the cleanup to give you the most accurate picture possible. So basically here you see like most of the contributions are going to be from individuals who are associated with Delta Lake at the time of the commit. And again, that the things to kind of keep in mind is that not Delta Lake's a little bit more tricky because again, not all of it is in that public repo because a lot of it was there was a time that Delta Lake was closed. There is a sort of a proprietary fork for Delta Lake that exists sort of separate in its own private repo. So there isn't sort of like full visibility into like the contributions in Delta Lake. And on top of it, like the way it seems like the way they do the repo is they group a lot of stuff off the public Git repo. So you might be seeing contributions that get grouped off, like merged on someone's computer, and then that person like merges it, and then basically it shows up as contributed to them. So it's a weirder setup there to get just to kind of point out the sort of like little nuances in sort of that picture. Okay, but either way you look at it, the vast majority of contributions are coming more from Databricks related sources. So again, going back to sort of like that playing field and just things to consider when you're thinking about the long run, am I going to have a variety of vendors to keep that competitive playing field to keep my cost low in the long run? Okay, we're towards the end here. Which is the right format to you? At the end of the day, like all these formats are going to be around. Again, and they're going to continue growing the features and continue expanding the performance. The data lakehouse is not going anywhere, and the data lakehouse is going to be the thing that, if not now, soon enough, we'll all have to really like spend a lot of time thinking about. Although I do think now is probably a good time to think about it. But you want to ask yourself, like, what tools do I use? Because I want to make sure that, hey, can the tools that I use support the format in a way that works for me? Like, do the tools I have the right performance with the format? Do they have the read and write support for that format? And so basically, you're going to want to do your own internal testing on your use case, okay? Not just go off, purely based off your decision off running TP-CDS on Spark on all three formats, because again, your use case is going to have different dynamics to it that are going to require that evaluation. Do I think I may change my tools or introduce new tools in the future? Think about what tools you're considering. Like if it's not a tool you're using yet, but is a tool with cool features and a cool roadmap that you're interested in going to go use in the future, okay, then you want to make sure that your format is compatible with those tools, because then that potential tool is no longer going to be an option once you double down on a format that doesn't work with that tool. How often will my schema evolve? Okay, which nowadays schema evolution is at parity, so that's a little bit less of a consideration. But does allow you to evolve your partitioning. That is still a consideration, again, through the differences in partitioning between the three formats. Okay, and again, especially if you have bigger tables, like petabyte scale tables, rewriting those are not a fun or cheap operation. So avoiding those rewrites can be quite a money saver. Okay, does the format enable intuitive and easy to use SQL syntax? That's another thing, like I think a lot of people take for granted. All three formats have SQL extensions. So you basically have SQL you can use to do a lot of the things in that format. But there are certain aspects of each one that are more ergonomics. The question is like, what are your typical patterns? So like, what are the kind of queries you think you're going to be running, and sort of which one's going to be the most intuitive for your team to use? Because it's a great thing to have a powerful tool, but if the tool is super powerful but not intuitive for your team, then you're not going to really get the most out of it. So you want to like, hey, take that trip down. Like, hey, what is the SQL? What is going to be the SQL dialect, and what's going to look like, and how intuitive does it feel? So that way we make sure that we're using this effectively. And again, it's going to be different from team to team. So just, it's a matter of just kind of going in there and taking a look at the documentation and getting hands-on with it. Is there a large and diverse developer community behind the project? And again, it's not just whether there's many people developing it, whether the code is visible. A lot of it's about the governance, because that's what's going to be what's going to determine the direction and sort of the openness, again, that playground and that even playing field. Who are making the decisions, and then how many sort of competing interests are there in the decision making to keep things sort of like fair and balanced. Okay. With that, we already talked about all that. And now we get to the Q&A. But before I start taking questions, what I want to say is that, again, thank you all for having me today. It's been great. My name is Alex Merced. Again, I'm a developer advocate here at Dremio, which is an open lakehouse platform. Okay, we do have support for multiple table formats when it comes to reading and writing to your data lake. So, one of many data lakehouse tools, and the benefit of the data lakehouse is because you can use many tools, and you have that big playing field of access to your data. So the data lakehouse is cool. But with that, again, you can follow me on Twitter at @amdatalakehouse, and with that, I will start taking questions. So let's see what questions are there. Is Iceberg more mature than the others? Now, far as I would say maturity, I would say all three of them are at production level, in the sense where people, big household name companies are using all three in production at petabyte scale. Like, that's happening. Delta Lake is probably the oldest of the three, so it's probably like, as far as like how long it's been around and its feature set, and some of the platforms that support it, like the most mature at the moment. But Iceberg is very mature. Like, again, people are using it in production. One of the big things you generally want is you're going to want some sort of platform that's going to help you sort of optimize the table, make it a lot easier to use that format. And in Iceberg, you're going to have a couple options. One of those being Dremio's Arctic service, which is currently in preview. So you can try it out for free right now. Highly recommend trying it. That actually gives you that whole Project Nessie Git-like semantics. So you can like branch your Iceberg tables and merge them. So that's available. Then like with Hudi, I think probably, I'm assuming OneHouse will probably provide service like that in the future. But with Iceberg, you have that, and you'll have a couple others that are out there that are going to be offering really cool services around Iceberg. So especially recently, you've had a surge of sort of companies getting behind Iceberg. And I mean, part of it is because of like sort of that even playing field. No one's dominating the project, so it gives anyone who wants to support Iceberg sort of like they have a chance to be like a player in the Iceberg world, instead of like second fiddle or something like that. And that's sort of like the appeal again of that open playing field, and why it's important, because in the long run that protects the things like cost. But Iceberg again has grown quite a lot, especially with it's gonna, with its most recent release, it really kind of cleaned up like the Z order, the merge operations on updates. So pretty much all the features are there, and people are already using it in big ways. So I would say all three projects are mature. I would say they still all have like the little like blind spots in the sense that they're appealing, but I think all three of them are good enough to be in production. But again, there's the different considerations depending on what your use case is. Okay, so let's see what the next question is. We do a lot of geospatial work and would ideally need something that could support spatial SQL queries like street within to point in polygon analysis. I think that's probably gonna matter more on the particular tools you're using. So like far as like having like geospatial queries, I don't know if any of the three formats currently support a geospatial. They probably a geospatial type as far as schema goes. But there are tools where you can have geospatial features that work with the table formats. So I think you can go with any format there. And if not, soon enough, that should be the case. And you should be fine. But I think that's going to be more tool driven than format driven. Typically, the data would have a geography column. Okay, I was just expanding on that question. You would recommend for us to review. We can play with these technologies on our laptop. I will look a little bit more into the geospatial thing. Like again, so I will follow me on Twitter at AMDA Lakehouse, because what I try to do is I try to do Twitter Spaces, like just little quick audio bits randomly to answer questions that I get, because I get all sorts of questions on all these formats. Because that's generally what I spend my days doing, is like reading up on the releases and the documentation for these formats and their different use cases. So I'm constantly doing Twitter Spaces where I'll just kind of expound on my thoughts. So do follow me on Twitter at AMData Lakehouse. Are features limited by file format, Parquet, Avro, or are they interchangeable? I think at the format level, they're interchangeable. So like you have the feature for all formats for the most part that particular format supports. What isn't interchangeable is whether the engine supports it. Okay, so you might have an engine that only supports reading Parquet files. So if you have an Iceberg table that's currently written in ORC files, well, that's going to cause a problem. So there's a lot of always the thing you want to look is you have all these tools. Each tool is going to be in a different place as far as how it supports the format as well. So you got to think, ask those questions part like, okay, hey, we plan on architecting our tables like this. Does this tool support the format? Is it going to be able to read the format with the files the way we have them written? Usually those are the two main questions. Like, can they read the file format? Can they read the table format? If they can read both of those, you should be in good shape. Okay. At what stage in a company should we use data lake technologies? I mean, my opinion at this point, getting started with the data lakehouse can be so low cost, like to get started up, that why not get started sooner than later? I mean, really, like you, for example, like you, and again, I don't want to sound like that guy, but just because this is the product I know, if you're using, let's say, like the Dremio cloud platform, like there's no cost to it, like it's free. Outside of like just any cloud compute, your cloud bill for AWS for any kind of clusters that you run for any queries, but even that can be pretty minimal. But I mean, the thing is that, so for example, let's say I'm a startup and right now I don't have data in S3 object storage. I mainly have it in Postgres or a MySQL database. But I want to start kind of doing analytics type work on it. I could open up a Dremio cloud account today for free and start getting some of that kind of infrastructure for that kind of scalable analytics right now. And then later on, when you want to kind of scale up and maybe start migrating some of that data to Iceberg tables, it's a matter of just making a create table as statement from Dremio, and your data is now in Iceberg format, and you're good to go. So, and again, your clusters are only running when you actually do work. So there's no cost to having the account. There's no cost to having it set up. So you can actually have that scalable analytics infrastructure pretty much right away and then use it as needed. So really the beauty of the data lakehouse is you don't